All right, greetings math people. Today's video is going to combine two of my favorite things. That's mathematics and track and field. So this video was inspired by an NCAA track meet I was watching. It was the NCAA Outdoor Championships. I was watching the 800. The 800 meters really is not one of my favorite races to watch, but it happened to be the race I was watching. And they were coming around the curve where they cut in, from the outside lanes to get into the inside lanes. And the commentator made something that kind of sparked my interest. So let me play the video.
Amon has gone 146.79 while his brother has gone in the 143s to lead the world.
They'll stay in their lanes until the backstretch, then cut for the pole. Again, the top two finishers in the next three fastest times over the three semifinals. So you really can't dog it here. And Clemson's Amon Thornton taking up the lead. Took the diagonal line right to the 200-meter mark, running the least distance that he possibly could.
So the commentator commented as the runner took the diagonal to the 200 that he ran the least distance he can run. And that kind of sparked a little interest in me because I ran track and field in high school. I never was an 800 runner. However, I ran the 4x400 relay. And on a 4x400 relay, we break at the same place. The second leg of the relay breaks at the same place. After you run the 100 meters, after you run the curve, you kind of break in. So we break in the second leg of the 4x400 meter relay breaks in at the same spot that an 800 meter runner breaks in at. And I just think back to when I was running, I was never really told what angle or where should you kind of break in at where you run the least distance possible. What I always just did, because I never got the baton in first place, is I really just broke in after I passed whoever was in front of me. I would pass everybody that was in front of me, and then I would break in. But in this particular video, we want to take a mathematical look at where is the best place to break in, either when running the 800 or running the second leg of the 4x4. Should you, as in the runner in the video, should you take the diagonal straight all the way to the end of the straightaway? Or should maybe you break in at 10 meters and then go, or maybe at 20 meters and then go? So we're going to take a mathematical look at where exactly you should make that cut in at. And when you get to the end of it, it's really something that can be done, fairly simply, but we're going to utilize a calculus process called optimization to determine where exactly is the best place to break in when running the 800 or the second leg of the 4x4 relay. So before we can tackle that, we have to get into a little bit of the dynamics of the actual 400 meter track to get an understanding of how we're going to work this out. And so there's a lot of mathematics embedded in track and field. The construction of the actual track field is very mathematical. How you should run certain races, what part of the lane should be in. So there is a lot to look at in terms of track and field and mathematics. So let's go ahead and begin and look at the anatomy of the track. All right, so what I have on the screen here is what is called a standard 400 meter track by the IAAF. And so that's the international organization that kind of is over track and field competitions, mainly the world competitions that you see. There's a world competition going to happen in Eugene, Oregon in a few weeks here. And this is not the only type of track that can be constructed. So, if you go to your local high school track, or maybe some community college track or junior high track, it may not meet these dimensions. So every track created does not go by these dimensions we're going to talk about here, but this is the standard track for international competition. And there are a few things when we go over this, there's a few misconceptions, that the lay person has about the constructions and dimensions of a track, and we'll debunk those here. All right, so we're looking at this diagram, and hopefully you can see. Let me put on my glasses so I can see. And I just want to point a couple things out. So there's a couple of misconceptions that some people have. One is that we all know that the track is 400 meters long. And some people think that the curves are 100 meters. So you have a curve here and a curve here. And then they think that the two straights are also 100 meters, adding up, of course, to give us 400 meters. But that's actually not how it is. So you can see here the dimensions. This is the straightaway here. The straightaway of a standard track is actually 84.39 meters. So it's not 100 meters. It's actually 84.39 meters. And the curve is actually a semicircle. So on a standard track, this is a true semicircle. Now, there are tracks, they're called double bend tracks, where this guy is not a true semicircle. In fact, it kind of changes at a certain point. And some of those double bend tracks, the straightaway is close to 100 meters. Some of them. Now, there's some where the straightaway is actually less than 84 meters, like 79 meters. So again, there's different constructions out there. So let's look at how we get our 400 meters, because that's something that's may not be understood as well. So we have two straightaways, which again are 84.39 meters. So we have 2 times 84.39 meters. And then we have these semicircles here. Now, of course, together they make a circle. And the circle has a radius of 36.5 meters. And so to get the distance of just the curve part, it's just a circumference of a circle with a radius of 36.5. And so that would be 2 pi times 36.5. And what happens, so if you do these calculations, 2 times the 84.39 is 168.78. And 2 pi times the 36.5 is 229.336. And when you add these two guys together, you don't really get 400, you get 398.116. So then is the true length of the 400 meter track 398.116? Sure, if you're measuring it right on this line. But that's not how they determine it, measuring right on this line. Because when you're running, you can't run right on that line. If you run right on that line, you'll get disqualified. So how the track is actually measured, there's something called a true running lane. Excuse me, why I just erase some of this. And the true running lane is actually measured from 0.3 meters away from the inside of the lane. So 0.3 meters away from the inside of the lane. Now, of course, if you're running the straight, it doesn't matter where you are. If you're just running straight, it's going to be 84.39. Whether you're right on the line or way out in lane 8, it doesn't matter. It's a straight. Of course, the distance matters for the semicircle part, because the more outside you run, the bigger the radius is. The bigger the radius is, the bigger the circumference of the circle. So, and there's a calculation to be made for each particular lane, but just for simplicity's sake, to give you an understanding, I'm just going to do this based off lane 1. And so the calculation is made with the true running lane, which is 0.3 meters from the outside. So that means that the radius of the true running lane is 36.8, not 36.5. We're going to add 0.3 to that, and we're going to get 36.8. So we'll have 2 pi times 36.8. And that will give us 115. Excuse me, That's for just one. That's just for one semicircle. For the whole guy, we're going to get 231.221. And when you add that to the number we got from the two straights, which again was 168.78, you get 400.001 meters. So this is the true length of the track when one runs a full lap from 0.3 meters away from the inside of the lane. So 400 meters, 400.001 meters. All right. So how's that going to help us determine where one should cut in the 800 and the second leg of the 4x4? Okay, great question. Well, we got to understand the dimensions of the track to be able to do these calculations. So there's one calculation that I need to tell you about that we haven't talked about, and you can see it on here. So if you notice here, they have this distance labeled as 9.76. And this distance is actually coming from lane 1 to lane 8. So that's lane 8 out there. I know it doesn't say, but trust me, that's lane 8. And we get that figure because each lane is 1.22 meters. And so multiply that by 8 and you get 9.76. So each lane on a standard track is 1.22 meters. All right, so when I do this illustration of where to cut in, you know, I can do it from any lane, except for lane 1, of course. If you're running the 800 or the 4x4 and you're in lane 1, you don't have to cut in, you're already right there. But now if you're running from any other lane, no, you have to kind of cut in. And so I'm going to do my analysis from lane 8, cutting in. Like, do I cut in there and run? Is that the best way? Do I cut in here and run? Is that the best way? Do I go all the way to the end like it appeared the runner in the video did? And is that the best way? So we're going to see which of those is the best way. Now, again, this is a calculus process called optimization. And so we have to set up a little diagram to figure this out. So let me illustrate where I'm getting these numbers from, why the diagram is still here, and then I'll draw it on a blank sheet. So the runner's going to be right here. So out here in lane 8. So it's going to create a little triangle where this length is 9.7. Part of my handwriting. 9.76. And he's going to run. You have this whole straightaway to go in, which of course is 84.39. And our question, of course, is where should they cut in to run the least distance? You know, should they just break right here and cut, or should they cut there? Should they cut there? Should they cut there? So that's what we're trying to figure out. So give me a blank page and let's construct this diagram. So I'm going to draw this again. So we got this guy, and this is 9.76. And this overall distance here is 84.39. And so these, so right angle here. So this is the cut in distance, like where does she cut in? I'll call it C for cut in, and I'll also call it C because it's the hypotenuse of a right triangle. And so after they cut in, wherever they cut in at, the distance that's left to travel, so let me call this distance right here A. Distance of the triangle right here A. So the distance that's left to travel after they cut in will be 84.39 minus A. 84.39 minus A. Hopefully that makes sense. This whole distance here is 84.39 and this distance is A. So this distance that's left is going to be 84.39 minus A. So the distance traveled, so when you do an optimization problem, you try to figure out what needs to be optimized. So what needs to be optimized is the distance traveled. And optimize can mean maximizing or minimizing. In this sense, of course, we're trying to minimize, finding the least distance. So the distance traveled is going to be, they're going to go C, and then they're going to go 84.39 minus A. So I'm going to write that as a function. I'm going to call it a function L. So L is C plus 84.39 minus A. Now, what we like to do is we like to write this as a function of one variable versus two variables. So we have, C and A. I want to have to just be one variable. So I'm going to rewrite this function just in terms of A. So what I'll do is I'll rewrite C in terms of A, which is pretty easy to do because, again, this is a right triangle here, and C is the hypotenuse. And from Pythagorean theorem, that tells us that C is going to equal the square root of A squared plus 9.76 squared. So that's C in terms of A. So now I can write the function L as simply a function of A. So I was going to erase some of this, but let me leave some of this because I'm going to make mention to it in a little bit. So I'm going to have this function L of A, where L of A is C, but remember C is this guy. So L of A is the square root of A squared plus 9.76 squared. That's just this part. And then, of course, we have this part. Plus, I'm going to have to erase some of this. Let's erase this little junk here. Okay. Plus, and I'm just going to write this again, 84.39 minus A. So let me get a little more room, just a little more erasing. All right, 84.39 minus A. Okay. So this is the function that we want to optimize, and we're trying to find the minimum value. We're trying to find the value of A that makes L the smallest value. Now, first thing we have to do is figure out a feasible domain for this particular situation based off A. So we want to find out what's the biggest A could be and what's the smallest A could be. And these will represent the endpoints of our function. And so we'll evaluate the function at its endpoints and at its critical points if it has any critical points. So an optimization problem is just like finding an absolute or global extrema. And to find absolute or global extrema, you evaluate the function at its endpoints and at its critical points. So that's what we're going to do here. All right, so let me just draw the diagram again so you can kind of understand what's the biggest A can be and what's the smallest A can be. So again, diagram looks something like this. And then we cut in there. And this was C. And this was A. And this was 84.39 minus A. All right. So let's talk about the biggest A could be. The biggest A could be would be, 84.39. A can't go past 84.39 because this whole straightaway is only 84.39. So the biggest A could be would be 84.39. Now, of course, if A is 84.39, then that's the scenario where the person cuts all the way across like that. So that represents the biggest A can be, which is 84.39. And of course, the smallest A could be would be 0. So if A is 0, then that's basically the person just shooting down right here, like coming from lane 8, going straight, cutting right in immediately, and then running the rest. Now that doesn't seem like the best thing to do from a running capacity, because you're, just imagine you're running straight and then all of a sudden you cut straight in and then run back. But we're not going to look at what's the best for running, what's the torque or the centrifugal force on a runner. We're just going to do it from a purely mathematical standpoint. And so, if something doesn't coincide with running a mechanical structure, we'll look at that a little bit later. But anyway, the smallest A could be is 0. So our feasible domain is 0 to 84.39. So 0 is the smallest A could be. 84.39 is the biggest A could be. So now we'll see if we have any critical points. So let me erase this down here. And a critical point, of course, is a value that makes our derivative either 0 or undefined. So we're going to find the derivative of our function L with respect to A. All right, so let's take the derivative of L. So this will be L prime of A. And so the inside is a little chain rule. So the derivative, not the inside, this square root part, that's going to require a little chain rule. So the first thing we'll do is we'll take the derivative of the inside part. That would be 2A. And then we'll take the derivative of the square root, which is 1 over 2 times the square root. So the 2 from 2A and the 2 from 1 over 2 times the square root are going to cancel. So we're going to have A over the square root of A squared plus 9.76 squared. The derivative of 84.39 is 0. And of course, the derivative of A is 1. So that's the derivative. We'll set that equal to 0. And then see if we can solve that puppy. Now, in order for this to equal 0, it will never be undefined, because our denominator, if you look, our denominator will never be 0. You have the sum of a square. That will never be 0 with real numbers. So we're going to try to find a value of A, which makes this equal 0. It won't be undefined. And for this to equal 0, that means that A over A squared plus 9.76 squared must equal 1. And for that to equal 1, then that basically means that A has to be equal to the square root of A squared plus 9.76 squared. And so if you just solve that, if you just square both sides, you'll get that A squared equals A squared plus 9.76 squared. And if you look, there's no such value of A that will solve this. If you subtract A squared from both sides, you'll get 0 equals 9.76 squared, but 0 doesn't. So this one has no solution. So there are no critical points to this equation, to this function, excuse me. So the function doesn't have any critical points. So that means the only thing we could do is input the endpoints into the equation. And of the endpoints, the one that gives us the smallest value, well, that's going to be the minimum. All right, so let's evaluate the function at the endpoints. So we're going to find L of 0 and L of 84.39. All right. So I've already typed the function in my calculator. And I'm just going to evaluate the function at different spots. So let me clear this. And L of 0 happens to be 94.15. And L of 84.39 that happens to be 84.9525. So, based on what we've done, as stated in the video, you would travel the least distance if you take the diagonal route to the end of the straight. So if you cut in like this, that gives you the least amount. And by a pretty significant margin, you know, compared to L of 0, because L of 0 should make sense. L of 0, you're doing this distance to 9.76, and it's simply the 9.76 plus the 84.39. And I mentioned early in the video that it's a very simple thing to understand this. That's a way simpler doing optimization, and that's simply that the shortest distance between 2 points is a straight line. So any other method other than going all the way to the end of the straight would not be a straight line. It would be two lines. Like if I cut in here, that's two lines. If I cut in here, that's two lines. So any other route other than going straight, hitting a straight diagonal to the end of the straightaway is going to be longer. Now you look at the two extremes. No one is going to be coming around on the second leg of the 4x4, come to the cone and shoot straight like this and cut in. So no one's going to do this. So you see a pretty big difference in these values. It's almost a 10-meter difference. And so no one's going to do that. But a lot of people, myself included, are going to cut in fairly early, maybe at 10 meters, maybe at 15 meters, maybe at 20 meters. And so it's important to understand the difference in the distances when you cut in like that. Like how much are you saving? How many meters are you saving by simply going all the way out to the straight versus cutting in at 10 or 20 or 30 meters? And if you look at it, so I'll do a couple of calculations here. I'll find L of 10, and L of 10 is 88.3635. So that's about 4 meters difference, almost a difference of 4 meters. Now that may not seem like much, but just imagine if someone is running a 400 meter or 800 meter for that matter. Think about if they win the race by 4 meters. That's a pretty significant margin. So it's a pretty significant margin of you cutting in at the end of the straight versus cutting in at 10 meters. Let's look at L of 20. So we can suppose that the longer you're cutting, the better. So L of 20 is 86.644. So almost a 2 meter difference. Again, still 2 meters is a pretty significant margin. And let's lastly look at L of 30. L of 30 is 85.6. So about a 1 meter difference on that. Again, still, and these races really with 800 meters has becoming somewhat of a sprint in recent years. A 1 meter difference is a pretty significant margin. So for all you track runners out there that run the 800 or run the 4x4 and may have to run second leg here or there, and you're wondering about what's the best way, where's the best place to cut in at once I go through the cones, that is to take a diagonal route to the end of the straightaway. That will guarantee you run the least amount, the least distance possible. Now, again, I did this example with lane 8. The same will be true for lane 2 and lane 3 and lane 4, etc. But the difference of the distances won't be as extreme. The closer you are to lane 1, the less of a difference this makes. So it makes an extreme difference for lane 8. It'll be less or so from lane 7 and lane 6, respectively. So I hope you enjoyed this video. We're going to have more math and track videos coming forward, being that this is a big championship season in track and field, and we'll see you next time.
Specialize in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe-to-toe, impeccable, splitting your back, son, simple as addition and subtraction, black thought, the infinite relax one.